Hi viewers, I am creating these videos to help teachers of maths support their learners in making sense of maths concepts and their associated procedures and processes. And today I thought I'd look at how we might introduce quadratic sequences to pupils. Now, some of this is obviously follows on from linear sequencing and how we might look at linear sequencing with pupils. So if you haven't yet seen my video around linear sequences, then it might be worth watching that first before looking at this, because we'll reference some of that stuff in this video. So if I'm introducing quadratic sequences to pupils, then I'll start in the same way as I start with linear sequences, by looking at or reminding them about the sequence 1, 2, 3, and the fact that this sequence is known as the natural numbers and we use the letter n to stand for it. And of course, the special properties of this sequence in terms of the fact that its positional number and its value are the same. So the first number, positional number 1 has value 1, positional number 2, the second number has value 2, and so on and so on. And you can see I've built that out of my algebra tiles here, 1, 2, 3, and so in general, a general length n. And then when looking at quadratic sequences, the first sequence that I will always go with, and the sort of obvious starting point potentially, is to look at the sequence 1, 4, 9, and how we build that from the numbers 1, 2, 3. And so if I'm going to look at this, I say, right, well, we've got 1, and that's fine, that's just a 1. And then if we're looking at 2, how might 2 become 4? Well, it might look like that. And then how might 3 become 9? And of course, it might look like that. And of course, pupils may well have studied square numbers by this point and be used to sort of the idea of when tiles can be arranged in a square like this, that we're going to be talking about the square numbers and recognizing potentially 1, 4, and 9 as the first 3 square numbers. And so what I might say to pupils is, okay, with your n's, build me something that exhibits the same pattern. And so, of course, what we're aiming for is this. We're aiming for them saying, well, that was a square of length 1, that was a square of length 2, that was a square of length 3. So in general, I'm going to need a square of length n. And then from there, so that this has nth term n squared. And then from there, what we might do is play around with that a little bit and say, right, well, then we know how n squared links to n. So let's see what happens if I change some things about n squared. Let's say I go with something like 3, 6, 11. What have I changed about n squared? And we might even be able to model that and say, right, well, turn that 1 into 3. I've done that potentially. And then to turn that 4 into 6, sorry, I've done that. And then to turn that 9 into 11, I've done that. And we can see that what I've done is added a row of 2 to the bottom of each one. So again, you'd be prompting pupils. You wouldn't necessarily point that out straight away to pupils, but you could be prompting pupils, okay, do what I did to all of my squares with your square. And we can see that I added 2 to that. Or what we might do instead is what we might do as well is, sorry, so this of course is n squared plus 2. Should have written that down before I deleted all of those. And we might look similarly at, using subtraction here and using a transformation on n squared that subtracts from each term. So I might go to 0 there, 3 there, 8 there. And so how did I generate those from these numbers? Well, to make 1 into 0, I did that. To make 4 into 3, I did that. And of course, potentially you might actually 0 pair those, but I want to be able to see the original 149. And to turn 9 into 8, I did that. So what would you do with the general square? And again, in the general square, we do that. And that's clearly therefore n squared minus 1. And, we can add several different things and look at several different things. So what about if I said, okay, what about 2, then 6, then 12, and so on? What might we be doing there? So to make this 2, I've added 1. And to make this 4 into 6, I've done that. And then to make this 9 into 12, I've done that. And so again, we might look at this and say, right, so come on then, guys, what did I do to each of my squares to generate this? Do that with your general square. And you can see here I've added a row of 1, a row of 2, a row of 3. In other words, I have added an extra row that is the same length as n, the same length as the n value there. So I've added this onto the bottom of that, this onto the bottom of that, this onto the bottom of that. So I'm adding this onto the bottom of that. And that gives me n squared plus n. But then as well as that, what I might do is come back to that and go, well, okay, that's what I did. Can you see these patterns in a different way? And this is potentially the first time that we might be able to see this in a different way. And we might say, oh, okay, well, actually, I can see this as a 1 by 2 and 2 by 3 and 3 by 4. And I can see that this rectangle is n by n plus 1. And if they're used to sort of expanding and factorizing, and pupils have had experience of that with the algebra tiles, they might recognize this because this is a rectangle, that it can be factorized. And the length of that is n, and the width of that is n plus 1. And we can talk about sort of the equivalence of those two expressions, n squared and n plus 1, having the same values all the time. And we can see that within the sequence. And, I can get ever so creative with this now. I can start throwing in all sorts of things. So let's say, well, look at what I do here and see if we can write down the nth term without actually having to write down the numbers in the sequence. And so I might do something like this and say, right, so look carefully at what I'm doing. What did I do? And we can see, oh, well, actually, you just created another square underneath the first square. I created another square that's the same size. And so, okay, well, what would that look like in general then? Well, in general, that would look like this. And we can see that that's got an nth term of 2n squared. Or what I could be doing is saying, right, well, watch what I do now. So I left the first one alone. What have I done now? And it's like, oh, well, you've added the previous square to the next one. So I added this square there, added this square there. Okay, well, what would that look like here? And we could be saying, okay, well, that's quite difficult to model, isn't it? But if I think about it like this, if I think about, okay, well, instead of saying I added the previous square, let's look at it in terms of this square and say, right, well, I've got like another one of those squares, but with 3 missing here. And here I've got another one of those squares with 5 missing. So what I've got is I've got like another one of those squares, but then I've got that bit missing there. And I've got this bit missing here, but now I've removed this bit twice. So I need to put that back in. And we can get some quite complicated sequences in this situation by looking out for the squareness and how we're adapting the square. And so eventually what I might do, I'm going to remove all of these now, but what I might do is start just building some patterns from scratch. And say, okay, let's have a look at what I'm doing here. So what am I doing there? Well, and again, there's potentially a couple of different ways I might look at that and see that, depending on how people have seen me build it. So I might look at that and go, well, I can see the squares. I can see the n squares there. So I've got my original n squares, and I can build that like that. And then what I've got is I've got 2 rows underneath each square, which are one more than the length of the square. So I've got 2 rows underneath each square, which are one more than the length of the square. Or alternatively, I might look at that and say, well, I can see the square and I can see 2 rows the same size as the square underneath. So 2 more rows of 1, 2 more rows of 2, 2 more rows of 3. And then I can see 2 attached to the right-hand side, which would give me, of course, the expanded form of that expression. And we can talk about the equivalences of these and things like that. Or what I might do is I might say, well, I can see a 1 by 3 with 2 more. And then I can see a 2 by 4 with 2 more. And then I can see a 3 by 5 with 2 more. So actually, as well as that, I can see a n by n plus 2 with 2 more. And again, we can look at that and see how all of these sort of expressions are equivalent, and both of these will expand to give this. Yeah, and so in general, I might be building that and saying, right, well, let's have a look at how you would build that. You might do that, and then that, and create that pattern that mirrors each of these in turn. And again, then we can look at this and say, right, well, let's write down what that pattern is. We've got an n squared plus 2 rows of n plus 1, or we've got an n squared plus 2n plus 2, or we've got an n by n plus 2 rectangle with 2 on the end. And what I'm trying to get pupils to recognize here is the squareness in this structure, the fact that there are squares appearing here. And what we might do with each of these sequences is, after we've found it, write down, okay, well, how many were in the first, second, and third? And then we might be able to look at sort of what these lists of numbers that are all quadratic sequences have in common, and come to this sort of idea of the common second difference that's going to be so important in actually forming a process for finding the nth term of a sequence from a list of numbers. But before I go through that process, and before I sort of take them through a procedure for this, what I want them to recognize and understand is around this squareness and this square structure, and how these things are all influenced by the fact that there is a square, or potentially more than one square, involved. So that is my short video on introducing quadratic sequences. As always, I would like to thank mathspot.com and its creator, Jonathan Hall, for this wonderful website, which I'm using to bring you these videos. And not only because it houses this wealth of virtual manipulatives that I can use to support bringing these videos, but also because of all of the other lovely things that it has. And if you are a teacher of maths and you haven't yet sort of had a look at MathSpot and all the wonderful things that it can bring to your practice, then I would strongly suggest doing so. And you will not be sorry if you have a look at that. And of course, if you are interested in visuals and manipulatives and representation in general to support teaching of maths, then I would suggest you check out my website. My website is visiblemaths.co.uk. And among the different things you will find on there, you will find a link to my book, Visible Maths. So that's why the website is called Visible Maths. And in the section about the Visible Maths book, you will find a few different links, but there's a link to the publisher there. The publisher is Crown House Publishing. And on their website, you can have a look inside at some of the sample pages from that book. And if you feel like it would be a useful addition to your library, then you can, of course, place an order. I have been creating these videos throughout lockdown, and I'm now continuing, hopefully, to create them beyond. So, and this is, I think, the second video that I've filmed since lockdown. So, I'm still trying to churn these out. So, if there is a particular concept or process or procedure in mathematics that you feel like you would want modeled, or to see how it might be, you might support pupils in seeing it using representations or manipulatives, then please do get in touch and I will try and get around to creating it for you. Thank you very much for your kind attention today.